Welcome everyone, my name is Krzysztof Suwada. I work currently at Brainly and I'm a Google developer expert in machine learning. This is quite a nice thing because Google can pay for many things for me. So if you ever want to become a GDE or MVP, you can reach out to me and I will tell you a few words how to become one. Currently I'm with Brainly. I've been told that here we'll have some students, also from the not only from the university but also from secondary school. So Brainly is a company based in Krakow. It's a Polish company, and it's the world's largest peer-to-peer learning community. And our mission is to inspire students to share and explore knowledge. And now we have more than 150 million unique users monthly. So this is quite a huge achievement for a company based in Poland. And Brainly is still a startup, but I hope that with your help, soon we'll have something more solid. So I really invite you warmly to visit our website if you are looking for answers, if you want to pose some questions. So today I'm going to talk about the NLP, so the natural language processing, what it is, how we can use it, what are the challenges. So first thing, computers cannot understand free text. They are extremely good with numbers. They are extremely bad with other things. So in order to make an algorithm or a computer to understand text, we have to translate it somehow to some magic number or a set of magic numbers. And as you will see, some numbers are better than others. So the question is how to represent a word. Second one, okay, let's assume that we already have some representation of the word. The second one is how to represent a sentence. Next, how could we represent an entire book or an article or tweet or whatever, you name it. This is a very tricky question, but we'll answer that in a while. The NLP is a pretty hard task, and you may wonder why it is so hard. And the question is very simple. We, as humans, we start learning a language since we are born, so it takes like 10, 15 years to master a language. So if you're 15 years old, you can say that you can speak pretty fluently, you can express your feelings, you can talk about different topics. And it took you pretty long. And as you can see, some languages are better than others, simpler. Better for me if I were to judge in terms of training an algorithm. This is one example, and this is another one. If you prefer Spanish than English, actually if you go to the United States, sometimes it's better to know Spanish than English. Comer, to eat. If you think that Spanish is easy and it is enough to represent a one word, to eat, to understand all the texts, let's see how many forms do we have here. It's all about eating. So it's not that easy. So the same concept, the same thing that we as humans naturally understand, that is something really, really obvious to us. For a computer, it can be pretty hard. Should I use the mic or not? Okay, I can use a mic if you... I'm not a big fan of it. The second thing is ambiguity. Because if I say I love Apple, I may refer either to the phone or to the brand. And the same thing applies, for example, Ted was bitten by the mountain. By the way, winter is coming today. So things that are obvious, that are simple, that are easy for us humans can be extremely, extremely difficult for algorithms and for computers. The other thing is dimensionality. If we, let's say, come up with some very simple representation of a text, like a bag of words or whatever, I will go to it in a moment, the number of words is extremely, extremely high. So in English language, we have more than 170,000 words. About 50,000 of them are not commonly used, so that's, okay, let's skip them. But anyway, it's more than 100,000 words. And if we include some connections between words, like not only new and not only York, but New York, it also it still increases. So we will have a lot of words in our dictionary if we want to make a word representation for them. So next thing is that some words carry more information about the topic than others, and also some words are more or less frequent than other. You could think that, let's say, a solution to the number of words would be just to put some kind of a threshold or a cap. So let's say if the word is not really frequent, that let's skip it, so just delete it. The same thing from the other end. If it's a very, very frequent word, still, let's do not bother about it because it most probably doesn't carry any information. But as it appears, it turns out, at the end of the day, you cannot really, just make arbitrary guesses. It's much, much better to have something else, like, at least try and see if you can prove what you're claiming is true. Another thing is that vocabulary is, in many occasions, is topic specific. So if you have some kind of a word representation for, I don't know, tweet classification, it may work just fine. But if you take the same algorithm or the same approach and you try to classify articles about quantum physics, oops, now it may not work at all. So it's a very, very tricky thing to make a good representation of the universe of the thing that you're working with. Another thing, mistakes. We, people, do mistakes. We make spelling mistakes. We sometimes use words that should not be used in the context. Like, we do not understand it properly, but we still use it. So, and then it comes into our data set, and another issue. Next thing, slang. Words that in other data sources, like, I don't know, academic or literature or poetry, means something else than in a real world. And an example from, I think, 2019, the youth word of 2018, dzban. So until 2018, I'm now 35 years old, so I'm not yet up to date with all the vocabulary, but I believe that I haven't heard about dzban in 2017, and now at the end of 2019, I have been called like this many times. So how can we represent a word? How can we represent a sentence? how can we force computer to understand text? First, the simplest, the easiest, the most natural solution is just simply create a dictionary, assign a number to each of the word, to each word that it has inside, just increase it by 1 each time you have a new word, and then just simply, for the sentence like the quick brown fox jumps over the lazy dog, we have a vector. So, O, 1, 2, 3, 4, 5, again O, because we have seen already before, so we didn't assign it another number, and we have our vector representation. Simply effective. But it has absolutely no information about the meaning of the word. It's just, it means absolutely nothing. And we as humans, and computers obviously too, tend to make some computations using numbers, not only using it as labels. So we'd like to somehow embed, this is why we have heard in the previous presentation, embeddings. We want to embed some additional information in that number, in that vector. So it's not only an arbitrary number, it carries more information about the word. So, another approach, one-hot and count encoding. So basically, we do more or less the same thing, but instead of assigning a number to each of the words, we just create a dictionary, and then to represent the sentence, we just create a vector of the size of the dictionary. So in our case, let's say, I don't know, 10 or 15, it doesn't really matter. And we put ones if the word from the sentence, if the word from the dictionary occurred in the sentence. So in this case, we'll have a hell of zeros, like 100,000 zeros and just a couple of ones, because usually our sentences are pretty short. It doesn't apply to my wife. This is the first approach. And the second one, we count them. So if the word appeared more than once, we just simply count how many times it appeared in a sequence. So in both ways, we already have a vector representation using numbers that computers can understand. And the question is if it's enough or if we can do something better. And the answer is yes, we can do it better. But now let's have a quick presentation about how it works using a real code. To do it, I will switch to something that's called Google Colab. Google Colab is a service provided by Google. It's free of charge. It's basically a notebook where you can run Python code. The main advantage of it is it's free, so you don't have to pay for it. The second one is based on cloud, so you can run it anywhere from any computer and it works. The other benefit it's free. It's really free. It has Python, Keras, TensorFlow, a lot of libraries already installed. And it has a GPU, so you don't really have to buy a GPU to speed up your computations, because you have one from Google and it's still free. It runs on up to 12 hours for one job to train, but you don't have to pay for it. You don't have to buy it. And another one, it has also TPUs, so there's something else is out of scope of today's presentation, but also can speed up computations, and it's again free. You can use TPUs for free. And it all, of course, if you have something more powerful or you want to train your algorithm for more than 12 hours, it can also be used as a UI. You can simply create a virtual machine using Google Cloud or AWS, or you can also connect to your computer and use Colab as an interface to that machine. Okay, so two simple examples. What I'm actually doing now, I'm just opening a file, a IPython notebook file from my Google Drive, and it opens up in a Colab environment, and just simply by hitting Shift-Enter, I got connected to an instance. As you can see that here, you can connect to hosted runtime or to local runtime. This one is hosted by Google. So I have been given a virtual machine for free, which I don't really have to pay for it. And another nice thing is that it has all the features that Google Docs has, so you can collaborate with other people who can share the code pretty easily. So this is really, really cool. So let's just simply run it. I will just increase the font. Tell me if you can see it. It's fine? Okay. So I'm using Keras for the time being. Now Keras has been incorporated into TensorFlow, if you're familiar with it. So Keras has been officially announced as a high-level API for TensorFlow. So which is kind of to because it really speeds things up. Maybe some of you are fans of going really, really deep, but to have a quick win and to have like a baseline solution, Keras is really, really cool. So basically what I'm doing here, I have a Python array with 2 sentences. I will just tokenize it, so I just simply divide it into some chunks, assign a number to each of the chunks, and this is my dictionary. So I simply number the words. I can do exactly the same for letters, because no one says that the vector representation should be based on words. It can, and sometimes it even should be based on characters. So something smaller than a word, especially for languages like Polish, where you have something like a root, and then you add some suffixes or prefixes. It makes totally sense to use this kind of representation, because the hidden assumption here is that the common parts share the common meaning, and this is why we should utilize it. So this is a very, very simple piece of code to create a dictionary and to parse text. And now a little bit more complicated example. We'll use the same approach to work on the IMDb dataset. So basically, if you know what an IMDb is, we have some reviews of the movies and we have some rating, and then we can try to predict if, after reading the review, if the assessment will be like negative or positive. There is a part that is too long, don't read. It contains some math formulas, so this is relatively boring. But at the end of the conference, I will share all the links and all the materials. So if you have time, if you want to, you can go through the code yourself. Basically, this is the idea, because we don't have time today to go line by line. So basically what I'm doing here, I'm doing the same thing I have just described. I'm creating a vector representation, and I'm feeding into a neural network, and I'm trying to assess if the review is positive or negative. And after some simple lines of code, I got a training accuracy of 85%, and the test accuracy is relatively the same. So we can say it's some kind of a success, maybe not a great one, but it's something that you can brag about among your friends. But what's more important, even with the simple approach, we already have something. It's better than random. So it means that this representation carries some information that can be useful. What can we do to make it better? So now we only either indicated if the word appeared in a sentence, or we counted it. So counting sounds like it's better because it carries more information. But it's only about a single sentence, it's about a single document, it's about a single tweet. So the next step is that we actually go through all the documents that we have in our database, in our data set, to see how frequent they are, not only among a document or a thesis, like, I don't know, PhD thesis, but among all other documents. So if you think about the word "the" in the English language, it's pretty common, so it doesn't really make sense to base our predictions on that because it doesn't really carry any information about the topic. For example, the Donald Trump and the nicotinamide adenine dinucleotide. This is the one and the only thing I remember about my biology classes from the high school. But I'm dreaming about it every night almost. So some words carry more information and actually have more discriminative power, are better. Usually, the words like that are less common. I mean, that they are common among documents about the same topic. Like the Donald Trump would be more common if we refer to politics, if we want to focus on the United States. But on Polish Twitter, most probably President Andrzej Duda would be something that has more impact. So how to incorporate this information? So as I mentioned before, the first one is how many times a token, a word occurred in a document. And the second one is how many times it appears in entire corpus, so in our entire data set. So if the word is very, very common in entire data set, it should be somehow weighted less because it carries less information. This is actually what TF-IDF does. This is term frequency inverse document frequency. So if it's common among a document, lift up. But if it's also very, very common among all other documents, then somehow we vote it down. But there is one catch. If we have very, very uncommon words, like they're very, very specific, this TF-IDF can explode. So usually it's also a good idea to put some cap on that, because like a professor on AGH University once told me, and this is a quote from him, in theory there is no difference between theory and practice, and in practice there is. So in this case, you should always check what the computer does for you, what the computations look like, what is the output, because in theory it should all work like a charm, and at the end of the day, we have a division by zero somewhere, and no one knows why. Another step would be to use not only words, but also something that's called Engrams. So basically, if we have a sentence, a token, a word will be just a simple single word. And if we want to use Engrams, we create somehow something like a sliding window, and then we have bigrams, like two consecutive words next to each other. And the word representation would be to first assign numbers to all of the words in the dictionary, then another number to all bigrams, trigrams, etc. And it's up to you to decide which one you want to use. If you want to use only Engrams, like bigrams or trigrams, or you want all of them. Why is this helpful? Because it, like New York, like Donald Trump, like President Andrzej Duda, it catches more information about the entity. And in many cases, it's a good baseline for classification text. It basically works better. We have a lot of documents, and the documents are larger. It doesn't really work for something like tweets because they are too short. There are many, many things that people have done over the years to make it slightly better. It highly depends on the tokenizer, so in a way, how you slice your document, which characters or which words you want to get rid of before you train your classifier. For example, if I decide that I do not want any numbers, I don't want like addition sign, I don't want exclamation mark, I don't want a dot, I don't want slash backslash, this kind of stuff, and I'm starting to work with mathematical formulas, not a good idea. And if I want to tokenize by space or a white character, and I'm working with, again, with formulas, with chemical formulas, again, it won't work at all. Another thing to mention, lemmatization and stemming. There are two things that can be used to somehow decrease the complexity, because then we are like this dwóch, dwa, dwoje, dwójka. We just simply replace all those occurrences with dwa, like that this is the same concept, and this decreases the size of our vocabulary and decreases the size of our vector representation, and sometimes may help. But it's not the state-of-the-art approach anymore for some years. And not for all of the languages it's easy enough to do this. Because, for example, for English language, the stemmers and lemmatizers are widely accessible. It's easy to get them. They work pretty well. But, for example, for Polish, no, not really. And what are word embeddings? We had a glimpse of an eye on embeddings in a previous presentation. So basically, we want to have a vector, a numerical representation of the word on which we'll be able to make mathematical operations and still pertain some information about what this word means. If it's a bad word, if it's about feelings, if it's about politics, if it's about history, if it's about mathematics, all those kind of things. I hope that you can hear. This is my son. Now he's 3 years old, but by the time I got this recording, he was 1 year and a half. And we were reading a Polish book for children. Nad rzeczką opodal krzaczka mieszkała kaczka dziwaczka. And we did it like, I don't know, 500 times or so. And at some point, he started doing things like that. Nad rzeczką opodal mieszkała kaczka, lecz zamiast trzymać się robiła piesze, reinforced learning. Raz poszła więc do fryzjera, poproszę o kilo. Tuż obok była apteka, poproszę mleka 5. So if it happened like 10 years ago, I could accuse Google of stealing an algorithm that got developed by my son. But unfortunately, he was born only 3 years ago. And the idea I'm going to talk about is called word-to-vec. This is an algorithm created by Google. You can find a lot information about it online. I will just only scratch the surface today because basically we could talk about it for more than an hour or so. Basically, the idea behind the word-to-vec is as follows. Let's say that we have a window of 5 words, like I've been saying, nad rzeczką opodal, and the next word is krzaczka. And the task is to train an algorithm that, based on words number t-1, t-2, t-3, t-4, will predict what is word number t, or the vice versa, based on like a context, based on a word, will try to predict the context. So on the left-hand side, this is the first approach, like my son just presented. We have to complete the sentence. And the approach on the right-hand side is something different. So basically we have one word, and we want to predict the context. So we have the same window, like 4 words, but the input on the left-hand side is the first 4, and the input on the right-hand side is just only a one word, like the center one. And the word representation here for the algorithm is very, very simple. It's just one hot encoding. So we have hell of a dictionary. So let's say 100,000 dimensional vector on the left-hand side with 4 ones, because we have only 4 words, and the outputs is the same, is a vector of the same dimensionality, but only with only one somewhere, because this is the word we are looking for. And inside there is a neural network, pretty simple one, not a convolutional one. It's not deep learning. Actually, they started with deep learning and with something very, very complicated. But then Thomas Mikołaj proved that it can be simplified, that even with a very simple approach, it still works. So this under the hood, there is a huge matrix of arbitrary size. I mean, the dimensionality of the vector representation is up to you if you want to train it. Like, let's say 100 dimensions. So how it works? Basically, we have a lot of text. We feed it to this algorithm. It learns, it tries to predict the next word in the sequence. When the accuracy is, let's say, quite okay, we just throw it away. I mean, not all of that, but we won't use this classifier anymore, because we are not going to try to predict the next word. We want to take what is inside. So basically, we take this huge matrix and use it as a word representation. Because what happened at the end of the day, when we finish our training, for each of the words that we have in our dictionary, we have one row in that matrix, which we can use as a vector representation of it. And the idea behind it is that the more dimensions, the more information it should catch. And what happens is that you can do math using those vectors. So, and you can look for analogies inside. So if we have words like man and woman and king and queen, if we take the distance between man and the woman, it will be pretty close to the distance between king and queen. Once more, if you take king, you subtract man, you add a woman, then the closest vector that you will find will be queen. So this is pretty cool. This is pretty amazing that you can do stuff like this, because it means that it preserved the meaning, the semantical meaning of the word. It's not only some magic number. It's not one hot encoding. It's not bag of words. It's something more that really catched at least something about the language. And this is without anything more than feeding text to the algorithm. So there was no one else that was saying that the king is also a man, but he wears a crown. It all happened magically, let's say. And the same thing applies to, for example, country and capital. It understands somehow that Spain, the distance between Spain and Madrid is something. And then if we add, we will do the same computation like Spain minus Madrid, we get the distance, and then we want to find words that are in the same distance for Italy, Germany, Turkey, and etc. We'll get the capital cities. So this is something, this was like kind of a major breakthrough for all people that want to work with text, because it allows us to get a complex, a dense representation of the text, not with 100 1,000 dimensions, but let's say with 100 only, that actually kind of works. And what's more, given the fact that mathematical operations work pretty well on those vectors, we have a way to represent something more than a word. Because at the beginning of the presentation I was saying basically that first of all we would like to have a vector representation for a single word, then for a sentence, then maybe for a book. And here, what we basically do is just sum up or basically create a mean value of it. So we have 10 words, we take 10 vectors, we actually sum them up, divided by 10, and this is the vector representation of the sentence. And you can try to do it with your own text. There are a lot of data sets that you can work with, for example, with IMDb data set. And the last example is that basically we'll take this notebook. I'm opening it in Colab, and let's run this example. Here I have created a neural network with simple recurrent neural network with a custom layer of word embeddings. So I'm not using a pre-trained embeddings from Google, which you can basically download if you don't have enough text yourself, but you still want to work to have a vector representation of the text. You can download pre-trained models from Google, from Facebook, from also other vendors. But here I'm training the embeddings myself. I'm again using the Keras IMDb. And here it's not about having amazing accuracy or having a great classifier that will tell me if it's positive or negative example. It's only just for a sake to show how it works. And for you to play around with the code later. Now I'm training the classifier, so I'm trying to classify those reviews, but the input to my network are raw texts. The first layer are embeddings. We are also get trained during the process using simple breakprop. And what I'm going to do, I will just get this first layer of my network, get the weights, download them to this computer. Actually, this one is not mine. And upload it to something that is also hosted by Google. It's a projector that allows me to see how those vectors look like in a three-dimensional space. So basically it can, having a vector of arbitral dimensionality, it applies a dimension reduction algorithm like PCA or TSNE, so you can see for yourself where those dots are on the plane or on the 3D space. And this is like a sanity check, because if it works, if those embeddings are fine, if they are something that we can work with, they should have words that are similar to themselves, quite close. And this is what you can do. And what is also nice about Colab is that basically you can easily upload and download data, which is usually cumbersome, and in this case it doesn't work for the reason I don't know. It doesn't want to fetch the data from the... Oh, okay. Maybe it doesn't work because it's Firefox. Oh, okay. Maybe it's on some other path. Give me 1 minute, I'll just fix it. The fix is pretty simple, just it should be like this. TMP. Oh, it should work like, okay. Okay, so now I have those files on my computer, and what I'm going to use is something that's called projector. There's something also provided by Google. You can basically do the same yourself on your computers. You're doing the PCA or something else, but it has some, it's a nice property that basically you can upload the data directly there, and then it creates also the visualization for you, and also you have a nice search on the right-hand side, which you can use. And this one, and this one. And here we have a PCA, so the principal component analysis. And let's type, I don't know, sad. Sad, sadly, sadness, sadistic, not really, or maybe, saddest. Makes sense, more or less. Queen, McQueen, Queens. Okay, maybe not perfect, but it's something. You want to try word of yours? What? Chair. Celebrity, activities, appointment. No, not really. So, basically, worst. Wasted, foiled, waste, insult, boredom, horrible, pointless, poorly. Fantastic. Delightful, smiling, quiet, greatest, specific. Cry, maybe not really, but maybe crying because you're, you know, it sounds so fantastic that I cried. This is only a test bed, so we have a limited data set, trained for a limited amount of time, like a couple of seconds, but we already have a vector representation that's somehow meaningful. I encourage you to go to tensorflow.org to fetch some more tutorials. You can try also pre-trained algorithms, get the vector representation from it, and try to visualize those embeddings. Because what Google did and what other companies do is basically you have a large corpora, you have a lot of text, you train for a pretty significant amount of time, and then the results are good. And one more thing, what I have mentioned before, that usually task-specific embeddings are better, the same applies here. So if you have something about, I know, educational, you have something about education, you have something about art, you have something about, I know, politics, maybe you would like to take those pre-trained embeddings and retrain them at least a little bit to adjust them for your task. Because at least I'm not aware of embeddings that are like for general use. There are some things like Elmo or BERT, but they were under-trained on purpose because they are meant to be used in an environment where you feed it with data yourself. Okay, so basically, that's all what I have for you today. And now I think this is the time for questions and answers, if you have any. Okay?
This word embedding layer is just a dense layer, or what is it?
This is just usually a linear layer, so you have it's like a lookup matrix for you.
Okay.
It also depends on what kind of embeddings you are using, but if you are training them for like in a word-to-vec, it's just, yes, but it is dense layer because it has to be connected to all of the words. And basically where you have, if you have words coming on the left-hand side, there's a one-hot encoding, vector encoding. What basically an embedding layer does, it simply replaces it with a vector representation of the word. This is why you feed it with raw texts. Okay?
Okay, so you mentioned the vector dimension reduction algorithms.
Yep.
And how do these work? Because if the dimensions are sort of like themes and how the word matches those, sort of. So how does that reduction method work?
For example, the principal component analysis works like this. Imagine that you have data in a, let's say, two-dimensional space, but it looks like a cucumber. So it's not like a sphere, it's more like a cucumber, but it's like with an angle of 30 degrees. So it's a pretty long cucumber, but still a cucumber. And it's not very thick, it's rather a thin one. So now you have a data that is represented in 2 dimensions, and you want to sacrifice some of those dimensions, in this case like 1, because this is the only thing we can sacrifice, but still with all the as much information as you can possibly have still remaining in this different representations. So in this case, you could, like, after performing a PCA, you get like for a 100-dimensional vector, you still have 100 dimensions, but the algorithm works like this, that the first, let's say, top k, in most of the cases, or in many cases, let's say out of this 100, the first 10 like still has like 95% of the information. So you can basically drop the other ones. So in this case, you are sacrificing all remaining dimensions, but the first 3 in order to create a visualization. And for the t-SNE, it's something a little bit different. The approach is different. In this case, you want to preserve the distance, the points that are close together in the high-dimensional space should be close together on the plane or in a 3D space. And this is basically the thing that this algorithm preserves, if I can explain t-SNE in one sentence.
Okay, thanks.
Another questions? Nope. Okay. So, thank you.